In 1966, two important things happened in my career as a physics teacher. First, I left university to take up my first teaching post, and second, the very successful Nuffield physics scheme was published, and I've used ideas from that material for the whole of my teaching career. This experiment is one of those, and it's concerned with mean free path. Now, a mean free path is the average distance travelled by a molecule in a gas between successive collisions, and we're going to use this simulation to represent this. This flat piece of paper is going to represent in 2 dimensions the 3-dimensional path of a molecule in space. And the 6 possible directions in 3-dimensional space are represented by the 6 lines coming from our original position of the molecule, which is there. Now we're going to use a dice to plot the path of the molecule for 25 successive collisions. And first collision, it's travelled to here. Second collision, it goes to there. So completely random. Third collision, it goes to there. Fourth collision, to here. Fifth collision, down to there. Sixth collision, to there again, where it gets difficult. So that's 6 collisions. Seventh collision, it goes back to there again. 8th collision, and that was a number 4, which is out here. Now we could sit here and watch me do the whole of the 25, but just to save time, I've done one of these earlier on, so we'll remove this one and put back my first attempt at this. And you can see there the mean free path, distance between collisions. Well, that's one of these lines on the grid, and that's 1 centimetre. The distance that my version travelled from its starting point A here to its final point after 25 collisions there was D. And I'll now measure it. I won't tell you what it is at the moment. Okay, you may better see what it is. There's a formula which states that this distance, the straight line distance, is equal to the square root of the number of collisions multiplied by x, the mean free path, which is actually 1 in our example. So the square root of our 25 collisions should come to 5 centimetres. And now I will admit to what my answer is. So not that close to the predicted theoretical answer. Now, does that mean that the theory is wrong? Does it mean that the experiment's not very good? Or does it mean that I wasn't very good at throwing the dice, or the dice is loaded? Well, in fact, none of those. All it means is we didn't take enough readings. And I think you should realise that if we took more readings, we might get closer to the theoretical results. And that is what I would like you to do, because you will have more time than I've got in making the experiment work properly than I can do in making the video.